we'll spend a few minutes reviewing the qualitative aspects of the photoelectric effect, the things that we talked about on Wednesday before we did our activity. And then we'll spend some time going into the mathematics of the photoelectric effect, do a couple problems with that. If you remember from Wednesday, the photoelectric effect was discovered in 1887, so almost 130 years ago, by Heinrich Hertz, by accident. He's doing some experiments with electromagnetic radiation, and lo and behold, he discovers that sometimes when light shines on a metal, an electron is ejected, or more than one electron is ejected. Why was that the case? Well, classical theory told him, and told a whole bunch of other people for the next 18 years, that electrons would be ejected if there was enough energy to eject those electrons. In other words, if the electrons absorbed enough energy, then an electron could jump to that higher level and leave the atom. Now, that made some sense. In fact, it still does make some sense. That part of the explanation was correct. We needed energy to cause the electrons to be ejected. Now, here's where the explanation, though, between 1887 and 1905 fell apart. In order to get more energy, according to classical theory, we need more light. So if a certain color of light is not causing electrons to be ejected, then what do we got to do? If we want electrons to be ejected, that is. What do we have to do? Get more light? Brighter light, right? Well, that's what classical theory for 18 years told us. That's what everybody that came up with an explanation for the photoelectric effect said, was that, look, if electrons aren't being ejected from this color of light, get more light, get brighter light. The problem is that never happened. If a certain color of light didn't cause the electrons to be ejected, it didn't matter how much of it we had, electrons would never be ejected. People noticed that sometimes another color of light or a higher frequency of light would cause the electrons to be ejected, but nobody could figure out why. Why did higher frequency cause it, but not more energy cause it? Well, here's the reason. It came down to the fact that higher frequency is higher energy. Okay, we talked about photon theory earlier this week. The energy of a photon is not related to its intensity. Rather, the energy of the photon is related to its frequency. So if you have, look, you want more energy to cause an electron to be ejected, okay, let's get a higher frequency. Higher frequency corresponds to higher energy. Similarly, the energy of a photon, Einstein said, is also equal to hc over lambda. So if you want a higher energy, and you're talking about it in the context of wavelength, we need a lower wavelength, a higher frequency or a lower wavelength. A couple terms we defined on Friday, or on Wednesday. Today's Friday. Defined these on Wednesday. The threshold frequency. Who remembers what the threshold frequency means? In this whole context of, electrons not being ejected below a certain frequency. I'm giving you a pretty big hint here. Josh? Very close, but not the minimum amount of energy necessary to eject the electron. The minimum amount of frequency necessary to eject the electron. So we'll say it's the minimum EMR frequency necessary to eject the electron. Any EMR below this frequency, nothing happens. Any EMR above this frequency, something happens. An electron is ejected. Now, we also talk about the threshold wavelength, but the symbol that we get for threshold wavelength is a little bit different. It's not lambda 0, rather it's lambda max. The threshold wavelength isn't a minimum wavelength, rather it's a maximum wavelength necessary to eject the electron. Because frequency is inversely proportional to wavelength, a min frequency will correspond to a max wavelength. The work function. The work function, real similar to what we have here. In fact, Josh pretty much already gave me a definition for the work function, right? It's the minimum, Josh? Good, good. The minimum energy necessary to eject the electron. The symbol, by the way, is W. The minimum electromagnetic radiation energy necessary to eject an electron. It also corresponds to the energy used up in the process. Well, that should make some sense to us, I think, right? If you have a certain amount that you need to eject the electron, why do you need that much to eject the electron? Well, because that much is used up in the process of ejecting the electron. Okay, so it's the same thing. Two slightly different definitions, but two definitions that correspond to the same thing. An equation for the work function. W is equal to Well, if energy is h times f, then minimum energy would be h times minimum f, right? The threshold frequency. Well, if energy is hc over lambda, then work function would be hc over lambda max. Now, this equation up here is on your data sheet. It's valid for the photoelectric effect, but it's also valid for any other situation where you have a photon, not just the photoelectric effect. The entire thing is on your data sheet. This one, part of it's on your data sheet. H times the threshold frequency is on your data sheet. It's valid only when you have the photoelectric effect. It's not valid in any other situation, just the photoelectric effect. Now, the last part of that equation isn't on there. So where are we going to get that from? Hc over lambda max. You're going to have to figure that out, okay? People tapping their heads, tapping their brains. You got to use your brains, right? If energy is hc over lambda, then W would be hc over lambda max, all right? Now, we also talked about what would happen if you had photons that were way above the threshold frequency. So you got an electron that's ejected when a photon exceeds the threshold frequency. If we exceed the threshold frequency by a whole lot, you're still going to get one electron ejected, right? It's a 1-to-1 ratio. One photon, one electron. 1,000 photons, 1,000 electrons. But if you're way above the threshold frequency, that one photon that causes the one electron, or the 1,000 photons that cause 1,000 electrons, okay, way above the threshold frequency, then the electrons will be more energetic. In other words, they're going to be faster moving. So the electrons will still come out in a 1-to-1 ratio. They're just going to be moving a lot faster than if we were just barely above the threshold frequency. Does that make sense? Finally, the last thing that we did on Wednesday, we defined this stopping potential. Stopping potential was the minimum, not the minimum, it was the potential difference necessary to stop an ejected electron. So an electron has been ejected. Okay, the photoelectric effect has already happened. We want to stop it. You stop it dead in its tracks. Why do we want to do that? Well, we'll learn a little bit later on today why we would want to do that specifically, but it has to do with finding the threshold frequency. Okay, if we want to measure the threshold frequency of a metal, and each metal has a different threshold frequency. If we want to determine what it is, then we're going to want to stop the electrons after they've been ejected, plot a graph, and calculate the threshold frequency. So we're going to say this is the potential difference required to stop an already ejected electron. Strictly speaking, this doesn't have anything to do with the photoelectric effect, really, right? Because the electron's already been ejected. It's already been produced. The photoelectric effect has already happened. We're just going to use this to collect some information about what's already happened, that photoelectric effect that's already happened. Finally, conservation of energy. This is not so much a definition. We know what this means, right? The total energy always remains the same. But we're going to derive an equation from the law of conservation of energy, an equation that you're going to need to use a lot, an equation that is not on your data sheet. Here's the way it goes. Well, we know that EI equals EF, right? We did that 1,000 times in physics 20. And we've already looked at it in physics 30 as well, right? Car going down a hill, car going up a hill. When we start this process, when a photon strikes an electron and causes it to be ejected, what kind of energy do we start with? What kind of energy do we have at the beginning of this problem? Kinetic energy? No. Potential? Not electrical, no. Elastic? No. Light energy or photon energy, right? The light strikes a metal. The light energy causes the electron to be ejected. So we start off with photon energy, HF, or you could say Hc over lambda. We'll remember it as HF, and then if we ever need to replace it with Hc over lambda, we'll do that. What kind of energy do we end up with? After this process has taken place, the electron's been ejected, what do we got? Kinetic energy. The electron has kinetic energy. We're going to call it EK max. EK max. Not EK, EK max. EK max is the maximum possible kinetic energy of the ejected electron. Why do we talk about the maximum possible energy? Well, because we don't really know exactly how much energy that electron is going to have. We can predict the most that it can have, but we can't predict the exact amount that it can have, right? Maybe you get a little bit of energy that's lost in some kind of process. Okay, so it's not the energy that it has, it's the most that it can have. We'll call it the maximum possible kinetic energy of the electron. And we're going to say that EK max is equal to 1/2 mv max squared. But we're also going to say that it's equal to Q times V stop. Because look, if you stop this electron dead in its tracks by the stopping potential, which we can do, then the kinetic energy would be converted to potential energy, electric potential energy, Q times V. Well, how much electric potential energy would it have? Well, Q times V stop. Because the stopping voltage is what was required to stop it. So we're going to write the equation like this. HF is equal to EK max. But if we need to replace HF with HC over lambda, we will. If we need to replace EK max with 1/2 mv squared or QV, we will. But there's something else in here. Remember, we used up energy in the process. So the final energy isn't actually quite equal to the initial energy. The initial energy is equal to what we have left at the end plus whatever we used up in the process. Does that make sense? Okay, if we started with 10 joules and we used up 3 joules, how much are we going to have left? 7. So 10 is equal to 7 plus 3, whatever we have left plus whatever we used up in the process. What's the energy that we used up in the process called? The work function. So HF is equal to EK max plus W. We might replace HF with HC over lambda. We might replace EK max with 1/2 mv squared or QV stop. We might replace the work function with H times the threshold frequency or H times C over the threshold wavelength. Or we might not. Depends on what we have given to us. This is a really important equation. Before they made a curriculum change a few years ago, this was on our data sheet. I liked it when it was on our data sheet because we use it a lot. Now they took it off. Not sure why they took it off, because we still use it a lot. But the good news is, it's not all that hard to derive. Okay, even if you forget the equation, it's not all that hard to come up with yourself. Let's try a problem here, 14.4 on 716. It says blue light shines on the metal surface. Who cares what the metal surface looks like, right? Shown on a metal surface and causes the photoemission of electrons. In other words, electrons are ejected. The photoelectric effect takes place. In other words, the blue light is above the threshold frequency. The blue light is below the threshold wavelength. There's a stopping potential difference, or stopping potential of 2.6 volts to completely prevent electrons from reaching the collector. In other words, to completely stop the electrons. We want to find EK max in joules and electron volts. All right, so what do we have here? This is going to be V stop, and we want to find EK max. We want to find it in joules and electron volts. Let's just summarize again real quickly what equations we have available to us and to use here. We have E is equal to HF is equal to HC over lambda. This equation is certainly valid for the photoelectric effect, but not specific to the photoelectric effect. We can use that whenever we want, as long as we have a photon. We also have the work function is equal to H times F0, HC over lambda max. That is specific to the photoelectric effect. Okay, we also have EK max is equal to 1/2 mv max squared, and it's equal to QV stop. Okay, that's specific to the photoelectric effect. And then we've got our conservation of energy equation. HF is equal to EK max plus the work function. That is specific to the photoelectric effect. Which of those 4 equations seems to fit this one the best? Back? Let's say EK max is equal to QV stop. What's the charge, Mac? Yeah, it's a charge of an electron. I didn't tell you that, but think about it. It's an electron that's ejected. So what charge are we going to use? The charge of the electron, same as any other electron. 1.60 times 10 to the minus 19 coulombs times the stopping potential, which is 2.6 volts. What do we get when we multiply those numbers together? 4.16 times 10 to the minus 19 joules. Now let's get that in electron volts. Say 1 electron volt, it's been a while since we've done this conversion, hey? 1 electron volt over 1.6 times 10 to the minus 19 joules equals X electron volts over 4.16 times 10 to the minus 19 joules. I'm going to take a wild stab at this, and I'm going to say that the energy in electron volts is 2.6 electron volts. Did I do that lightning fast calculation in my head correctly? Or did I just kind of cheat? How did I know it was going to be 2.6? Well, I don't remember the answer, but I still cheated though. Yeah, I just multiplied 2.6 by 1.6. Now what am I doing? I'm dividing it by 1.6. What am I going to get? Of course, the same thing, right? If you're dealing with an electron, the volts and the electron volts will always be the same number. But if you're dealing with an alpha particle, it won't be. So my suggestion is don't remember what I just remembered. Okay? Tanner said, I've done this a million times before. Yes, I have. I didn't remember the answer, Tanner, but I did remember that when you're dealing with an electron, you're going to end up with the same number. Okay? I would suggest to you, don't try to remember that. If you happen to remember it, that's great. Don't try to remember it, because you might get confused if you try to remember it. Okay? Just do it like this each time, because in the end, it's always going to work out. All right? I'm going to give you literally just a couple of minutes to work on these questions, and then we're going to do another example. All right, we're going to move on here. Doesn't seem to be any big problems with these. If you haven't quite finished them, then let's finish them up for homework for Monday, please. We're going to move on to another example here. 718, 14.5 says, experiments show that the work function for cesium is 2.1 electron volts. Of course, every metal has a different work function. Okay, if we're doing building some kind of solar cell, whatever, we might want to know what the work function is. Okay, you don't want to design something that has a work function that's in the range of X-rays, because that's not going to be a very effective photoelectric producer here. Okay, so we might want to know what the threshold frequency is and the work function is. For cesium metal, 2.1 electron volts. We'll circle the electron volts because we don't normally like electron volts. Let's write that down as a W. Okay, the threshold frequency is what we're looking for, and we're looking for the threshold wavelength as well. So we're going to call that lambda max. Okay, let's look at these 4 equations again and identify which one or ones seem to fit this the best. Which one do you want to try for this? The first one, which we can use whenever we want, as long as we have a photon, or 2, 3, or 4, which are specific to the photoelectric effect. Who's got an answer for this? Kelsey, is your hand up? The second one? Okay, let's try. W is equal to H times the threshold frequency to get F0. F0 is equal to W over H. Do we have to convert that to joules here? No. Can we convert it to joules? Sure we can. Okay, if in doubt, go to joules. Okay, it always works. But in this case, we can stick with the electron volts as well. But if we do that, we got to stick with our Planck's constant that's in electron volts. 2.10 divided by 4.14 gives me 5.07 times 10 to the 14 hertz. Now, you got a couple of options here, actually, to find the threshold wavelength. What's one of them? What's the most obvious option at this point when we want to find the threshold wavelength? W is equal to HC over lambda max. Okay, and that's absolutely fine. Okay, we can do that, right? Just solve for lambda max. It's HC over W. Same deal with this one, right? Be consistent with your units. The other option at this point is to say V is equal to F times lambda. Lambda is equal to V over F. What's V? 3 times 10 to the 8. What's F? 5.07 times 10 to the 14. Okay, so either way works. Okay, this is, about 4 seconds quicker than the other method, than this method, but it doesn't make any difference. All right? We're going to give you, again, just a couple of minutes to work on these questions, please. How are we doing with these guys? Anybody struggling a little bit with number 2? Yes? Should we go over number 2? Who got it? Good. Good. Let's take a look at number 2, okay? Blue light of wavelength 410 nanometers. That's our wavelength. We keep circling this nanometers because it's non-standard units, but we're getting pretty used to seeing that, right? Nanometers occurs often when we're talking about light because that's that range of visible light. The work function is 2.10 electron volts. We're going to circle that as well, even though we know that we can often use electron volts. We want to find the energy of the emitted electron. What kind of energy does the electron have once it's emitted? Kinetic. So we're going to look for EK max here, right? Now, which one seems to fit? E is equal to HF, HC over lambda. We have lambda here. Problem is, that's not EK max. That's the energy of the photon, not the kinetic energy of the electron. So that's not going to work here. This one doesn't say anything about EK max in there. This one seems to be the one we want, except we don't know what V is or V stop is. Let's try this one. If in doubt, you're not sure where to go with the question, go with the last equation. Go with the one that doesn't appear on your data sheet, because it's the one you're probably going to end up using most often. HF is equal to EK max plus W. All right, let's try this now. We don't know what F is, but we can replace F with C over lambda. So HC over lambda is equal to EK max plus the work function. Make sense? Because HF is same as HC over lambda. What do you want to use here? Electron volts or joules? Electron volts? Okay, we can do that. I'm going to show you in 2 seconds, though, a situation where you can't. Lambda is 410 times 10 to the minus 9. And the work function is 2.10 electron volts. Okay, when we do the math on this one, we end up getting, is that the right answer, not 0.932? Yes? Actually, you know what? I think I remember from last semester, actually, I think I remember this question. The answer in the book was wrong. I think it is 0.929. 0.929 electron volts. Does that work? All right. Okay. Pay really close attention to this and write this down somewhere, okay? We're allowed to use the electron volts in this problem, but if we use 1/2 mv squared or QV, we must use joules. So in this question, we didn't have to use 1/2 mv squared or QV stop, but we were close. We used EK max, right? We used EK max. We just didn't sub in 1/2 mv squared or QV stop. If we were looking for the maximum speed of the ejected electron or the stopping potential in this question, then we would have had to introduce QV stop or 1/2 mv squared, and then we would have had to use joules. Okay, if that confuses you at all, what should you do? If what I just said confuses you in the slightest, what should you always do? Just use joules, because it always works, right? Electron volts has worked for every question we've done so far, but you can see now a problem where it wouldn't work. Neil? Oh, okay. Okay. If you use joules for this one, okay, Neil said he used joules for this one and ended up converting back and got 0.932. Okay, interesting. So we got 0.929 using electron volts, 0.932 using joules. Never realized that would happen, actually. What do you think the problem with that is? The constant is rounded. 4.14 is a rounded number, so is 6.63. So they're going to give us slightly different answers. Don't worry about that. If this was a diploma exam question, both of those would be marked correct, okay? That's checked over by enough people before the exam is made that somebody would have thought of the two different methods for using it, so you don't ever have to worry about that, okay? 0.932 or 0.929 both would have been keyed correct. All right, let's do one more. Last one here today. 14.6 on 719. So it's using table 14.1, determine the max speed of electrons emitted from an aluminum surface if the surface is illuminated with 125 nanometer light. This is going to be lambda, not lambda max. Okay, we're not saying this is the threshold wavelength. We're just saying this is the wavelength of the light that we're shining on it, which presumably is below the threshold wavelength and is allowing electrons to be ejected. Table 14.1 gives us work functions, I believe. Somebody look up on 14.1 what the work function of aluminum is. Thank you. Thank you. It's 4.08 electron volts, and that's going to be the work function. We want to find the max speed. All right, which one do you want to use? 1, 2, 3, 4, 5. 2 seconds here, guys. Just pay attention for a couple more seconds. I counted to 5. Nobody gave me an answer. Okay, listen. If you don't have an answer within about 5 seconds, go with the last one, because it's likely the one you're going to use if it's not immediately obvious. So let's say HF is equal to EK max plus W. Let's replace HF with HC over lambda, because we've got a wavelength here, not a frequency. EK max, well, that's equal to 1/2 MV max squared, since we want to find V max, right? Plus the work function, well, we've got that. What do you got to do here? We got to use joules. We have to use joules. So we're going to need to convert that to joules. And we're going to have to use what value of Planck's constant? 6.63 times 10 to the minus 34. Does that make sense? All right. Your homework for the weekend are those 3 sets of questions, if you haven't finished them already, including page 719 that you're just seeing for the first time now, okay? Yes, there will. Yeah. Have a good weekend, everybody, and we'll see you on Monday.